So this is very similar to, again, the calculations that you'll have to do today in this experiment, and obviously in lecture as well. So let us take a look at perhaps the first one here. Get something to write with here. That might help. Try that. There you go. All right. So we basically have an electron that's transitioning from the n equals 5 energy level to the n equals 2 energy level. And again, just for orientation purposes, n equals 5 is higher in energy, obviously, than n equals 2 is lower in energy. So this electron is traveling down in terms of energy. And we'll see what that all means in just a second. So whenever we're trying to figure out the energy associated with that, we're going to use that equation that we saw in lecture at the end there. The change in energy is minus 2.18 times 10 to the minus 18 joules. I'm going to round that number just to make it a little bit easier. 1 over n squared final, so the final guy, minus 1 over n squared initial, so your initial energy level. So we could calculate right off the bat the change in energy here, going to be minus 2.18 times 10 to the minus 18 joules. Our final is actually 2 here, right? So that's our final. So 1 over 2 squared is 4, 1 over 4. And 1 over our initial, which was 5, will do 25. I'll actually square it this time. I think I didn't the first time. And if we do all that good stuff there, we're going to take 1 divided by 4 minus 1 divided by 25 and times it by 2.18 to the minus 18. Looks like it will get us something like, we'll go 4.58 times 10 to the minus 19 joules, and it will be negative in this case. And that makes sense as what we were just talking about. Again, that electron is going from higher energy to lower energy. So what it has to do is give off that energy in the form of a photon. And that would mean that it is exothermic in this case. Again, negative value for our energy. Any questions so far on that particular one? Now, we want to also find the wavelength and the frequency. So remember that our E here is equal to H times the frequency. It also equals HC over the wavelength. And it also equals, obviously, this number here. So we can use our E is equal to H times the frequency. This is one way we could get the frequency. And that means that the frequency would be E divided by H when we divide the H to the other side. Now, this is what I was talking about previously at the end there. Our energy is negative, and you should leave it as a negative number for the energy value. But when we continue on to use it here to calculate something like frequency or wavelength, we want to get rid of the negative so we do not get a negative value. So we're just going to use the positive version here, 4.58 times 10 to the minus 19 joules. We're going to divide it by Planck's constant, which is that 6.63 times 10 to the minus 34 joule seconds. Joules are going to cancel each other out, going to leave us with reciprocal seconds, and that will leave us with divided by 6.63 minus 34. Looks like we get a frequency of 6.91 times 10 to the 14. Again, here reciprocal seconds, which is a hertz, would be our frequency in this particular case. Now, because we now have the frequency, and honestly, we have the energy as well, to get to the wavelength, you could really do it two ways. You could use E is equal to HC over the wavelength, and the wavelength equals HC over the energy. Or because we now have the frequency, you could also use C is equal to the wavelength times the frequency. R, the wavelength, is equal to C divided by the frequency. I'll do it both ways here so you can see you should hopefully get the same answer. So if you did 3 times 10 to the 8 meters per second, which is C, divided by our frequency, which is 6.91 times 10 to the 14 reciprocal seconds, we will end up with 4.34 times 10 to the minus 7 meters. And remember that we want to go to nanometers, so there are 10 to the minus 9 meters in a nanometer. So we want to divide that by 10 to the minus 9, or 1 times 10 to the minus 9. And again, you want to make sure you use your exponent button, get you 434 nanometers as our wavelength. Again, here you could have went into this one as well. And this would be the wavelength is equal to our Planck's constant, joules seconds, our speed of light, and through our energy in here, also making sure you use it as a positive number, not the negative number. Joules will cancel, seconds will cancel. We'll leave you with meters at that point, and what you will get is hopefully the same number.
Do you always want wavelength and nanometers?
Not always. In this particular case, we do, because we're talking about the visible part of the spectrum. So it usually is very commonly in nanometers in this case. If it really doesn't specify, you can leave it in any unit you want. But that's usually why we kind of went to nanometers here. And then obviously we got the same number, as you can see, and it would convert obviously into the same number in terms of nanometers. Questions on any of that?
Going back to frequency.
Yeah.
Is it ever negative?
No. So you always want to make sure the frequency and the wavelength should always be positive numbers.
Okay.
And what usually happens is people forget to get rid of the negative there on the energy, and that's where they usually end up with that negative value. So it is important, though, like I mentioned, to keep the negative on the energy, because it does indicate whether or not it's exothermic or endothermic in terms of the energy part for the atom. But you definitely should just make it a positive number if you're going to carry on with it to do something like wavelength or frequency. And those should always be positive numbers. Yeah. Other questions? So just for reference point, in terms of 434 nanometers, if you kind of look in the visible part of the spectrum, we're shooting like blue in terms of that color. So this is a blue. All right, let's take a look at the next one, which should be a very similar type calculation here. For B, we're going from n is equal to 4 to n is equal to 2. So we'll start with the same part of the calculation there. We're going to use that energy equation and our final minus initial to figure out the change in energy that's really happening with the atom. So again, here we are going from 4 to 2. So that's higher energy level to lower. So much like what we saw in the previous one, we could predict that the energy change should be negative here for our atom. So minus 2.18 times 10 to the minus 18. Our final is our 2 here. So again, that's going to be 1 over 4. Our initial is going to be n equals 4. So 4 squared is 16. And if we do that, we'll get 1 divided by 4 minus 1 divided by 16 times 2.18 to the minus 18. That's going to give us an energy here for the atom, again, minus, which is what we predicted, 4.09 times 10 to the minus 19 joules. So again, here we do want to keep the negative for our energy, because that tells us, like we would predict, again, the electron is dropping energy, which means for the atom, it's got to give off that energy. So it'll be exothermic for the atom there. And again, that's why we have that negative number happening. And here again, we have a couple of ways we could get to the remainder of the answers. We again could do the same thing for the frequency. E is equal to h times the frequency, which means the frequency is energy divided by Planck's constant. So here again, we're going to get rid of the negative, because we want to make sure that we do end up with a positive number. And our H again is a constant 6.63 times 10 to the minus 34 joules times seconds. Again, the joules are going to cancel. That's going to leave us with our reciprocal seconds. And as I mentioned earlier today, you want to definitely make sure you are using your exponent button on your calculator, or again, you will be finding yourself like off in terms of your numbers. So again, if your numbers are very close to the front part, but this part not so good, probably the way you're putting it into your calculator. So we get 6.17 times 10 to the 14. Again, the units here are reciprocal seconds as our frequency. And lastly, at this point, now that we have the frequency, for example, we can use this equation here if we like to figure out the wavelength. The wavelength would be C divided by the frequency. So again, C being a constant, 3 times 10 to the 8 meters per second, divided by our 6.17 times 10 to the 14 reciprocal seconds. Again, our seconds going to cancel, and this will give us our wavelength in meters. And if we do that, looks like we get something like 4.87 on some rounding times 10 to the minus 7 meters. And again, here, since we are in the visible part of the spectrum and talking about colors, we want to convert it to nanometers. So again, 10 to the minus 9 meters is a nanometer. And we would divide that by 1 times 10 to the minus 9. And that's going to give us 400, and we'll round it to 487 nanometers as our wavelength. Any questions on those there? And again, you might end up with 486 if you did a little bit more rounding than I did. It's okay. And in terms of color, this is somewhere near green in terms of color, where it's coming off. Any questions on that particular one?
Do you always convert it to nanometers at the end?
You don't always have to convert it to nanometers. Typically, if it's in that visible part of the spectrum, so that visible part of the spectrum is where we see color, right? So that's where that rho RGB is. And typically when the wavelength's given for that part of the spectrum, because they're kind of small numbers and used a lot, they're usually given in nanometers, but they don't have to be. So again, if it doesn't specify, you could have left it in meters. It would have been perfectly fine.
Okay, thank you.
You're welcome. Other questions? Okay. So one last one there, where we are transitioning from, where are we transitioning from? We are going 3 to 2 here. So again, following sort of the same thing we've been doing, n is equal to 3, n is equal to 2. So still the same sort of transition going down in energy. So we can predict that our energy here should be negative for the atom, as it should be given off that energy to allow the electrons to drop down. And rolling through our calculation here, minus 2.18 times 10 to the minus 18, which again is a constant. That's that Rydberg's constant, in case you ever need to find it by name. Our final here is going to be 2. So 2 squared will give us 4, minus 1 over our initial squared, which is 3. So that's going to be 9 in terms of squaring it. So 1 divided by 4 minus 1 divided by 9 times 2.18 to the minus 18, going to give us 3.03, also going to be negative here, 3.03 times 10 to the minus 19 joules. And again, as we talked about there, negative, which is what we would expect to happen. And we will then go with the frequency like we've been doing. So E is equal to H times the frequency. So our frequency being E divided by H. And that's going to give us, again, using the positive value here, divided by our constant. Again, joules going to cancel, going to leave us with reciprocal seconds are a hertz. And 6.63 minus 34. Going to give us 4.57 times 10 to the 14 Reciprocal seconds are the same thing as a hertz. And again, here, one way to get to wavelength is to use the same one that we've been using. Again, just like we did on the first one, you could, if you wanted to, just went right to wavelength using that one as well. And again, wavelength here would be C divided by frequency. So 3 times 10 to the 8 meters per second, and our frequency of 4.57, 10 to the 14. Reciprocal seconds, seconds going to cancel. And we will end up with, looks like 6.57 times 10 to the minus 7 meters. And again, doing our conversion to nanometers, since I asked you to do that, and you'll have to do that a lot in this lab as well. We're going to divide it by 10 to the minus 9. And it looks like we end up with 657 nanometers here. And for reference, that is sort of red, orange, red type color. And in terms of the other question that was actually asked is what transition resulted in the longest wavelength of light? And that would be our C transition. Our C transition had the longest wavelength, 657 nanometers versus, I think it was 486 versus 434. And again, we would expect that based on what we talked about, this transition is one energy level, which is the lowest amount of energy of all three of those transitions that were there. Lowest energy should correspond to longest wavelength. The shortest wavelength, which is the 434 transition, the 5 to the 2 should also result in the highest energy, right? Because that's, again, shorter wavelength, highest in energy, also probably should be highest in frequency as well in terms of that when you compare the numbers. So again, any questions on any of these sort of calculations? Clearly, you need to be able to do these calculations. The lab for tonight is pretty much all these calculations, a whole bunch of them. Any questions on any part of that? And as you can see, there are some multiple ways you could calculate it. For example, for the wavelength, you could use the energy value if you want. You could then, or get the frequency like we did on some of these, and then get the wavelength, you know, whichever way you want to kind of do it. You could alternatively get the wavelength first and then get the frequency. So you could do it that way as well. So there are a few different ways you can kind of get there. Again, providing that you punch all these numbers in correctly, you should end up with the same number no matter which way you went. And again, if you're finding yourself off on any of these numbers, especially the exponent part, my guess is it's how you're punching it into your calculator.